I'm just going to do a quick screencast of 1.1 and 1.2 for AP Chem because I know you can't get to it, but I somehow can. So I'm going to go ahead and be quiet and let you just watch what's on the screen, and you tell me if it works. Okay.
Ice cube, liquid water, water vapor. Do the substances look different to you? Look closely at an ice cube and a glass of water. In both substances, the molecules are the same, but the arrangement and behavior of the molecules are different. You may have wondered what causes ice to maintain its shape, while liquid water flows easily. You're about to discover why different substances such as ice, liquid water, and even water vapor behave the way they do. You will also investigate the concepts behind the properties of different types of matter. Let's dive into the waters of intermolecular forces.
I will send the reading guides to you somehow. I don't know which one you use. But I will get them to you. Hopefully they're both saved down here. Nope, only one of them. I'll just save them both as PDF. Sorry, this is all new to me. I'm just trying to work it out so you can work on this and not feel like you're getting behind. So I'm going to go ahead and get you both of these, send them to you. Okay. So we're going to read that, and then I guess I can show you the quiz. Each one's worth 2 points. You get 1 attempt at each question. So, I can't record your grade, but I can show it to you, I guess, I think. Maybe not. It's not letting me do that. No. But I could just print it off for you, but not sure how to do this. So here's intermolecular forces, big ideas. And I'll go ahead and record this video so you can see it.
Hey there! You're familiar with water, right? Of course. It covers most of the earth, and you can't live without it. I'm going to use a penny to show some of the reasons water is so special. Yep, a penny. We have some water, vegetable oil, and isopropyl alcohol. A little food coloring was added to the water and the alcohol just so we can see them. What do you think is going to happen when I place a drop of each liquid on a penny? Will the liquid spread out or not? Let's find out. First, the water. Next, the isopropyl alcohol. And finally, the vegetable oil. The water and the alcohol form beads, but the oil spreads out. Why? The water molecules stick together because of the intermolecular forces between them. The surface tension makes the water bead up. The water molecules are more attracted to each other than they are to the surface of the penny or to the air. So let's try that with the alcohol. The forces between the molecules in the isopropyl alcohol solution also cause this liquid to bead up, but it can't form as big of a drop as water. The intermolecular forces are not as strong as they are in water. And then there's the vegetable oil. I'll see what happens with that. It just spreads out. What does that tell you about the intermolecular forces in the veggie oil versus those in the water? I told you water was special.
Now I got to figure out how to page through. So do I just put in page 2? Go. Okay. I'll just pause so you can take a look and read. If I go too fast, just pause the recording.
Water has polar bonds. The oxygen and hydrogen atoms in a water molecule are held together by covalent bonds, which means that the atoms share electrons. Oxygen is bigger and pulls on the shared electrons more than hydrogen does. So even though these atoms share electrons, they do not share equally. This unequal sharing results in what is called a polar bond. Because oxygen is hogging the electrons, this makes the oxygen end of the molecule slightly negative and the hydrogen ends slightly positive. Having positive and negative ends makes water a polar molecule. Because polar molecules have slightly positive and negative ends, polar molecules are attracted to other polar molecules. The positive end of one water molecule is attracted to the negative end of another water molecule. This is why water sticks to itself. Water molecules are attracted to each other.
By now you know that the intermolecular forces in water, in isopropyl alcohol, and in vegetable oil are all a little different. Those forces affect the types of solutions you can make. Let's take a closer look. First, you might be thinking that rubbing alcohol is not pure isopropyl alcohol, and you're right. It says so right here on the bottle. Isopropyl alcohol, 70%. That means rubbing alcohol is a solution of 70% isopropyl alcohol and 30% water. Water and alcohol are miscible liquids. Miscible means that two liquids can dissolve in each other in any amounts. Water and alcohol mix so well because both types of molecules can form hydrogen bonds. You've probably heard of the rule, like dissolves like. It means polar molecules dissolve other polar molecules, or nonpolar molecules dissolve other nonpolar molecules. You can use the rule to predict that the nonpolar molecules in oil won't mix with the polar molecules in water. Oil and water are immiscible. They don't mix. The rule can also help you decide which forces are at work in an unknown substance. Let's try food coloring in water. Food coloring spreads out in water to make a solution. It's miscible. What do you think will happen when the food coloring is added to oil? It sticks to itself. What does that tell you about the molecular interactions between the molecules in the food coloring? Awesome stuff, huh?
You heat a solution to evaporate it. Each part of the solution boils at a different temperature, so as one boils, it is collected. Because each boils at a different time, the different components of a solution can be separated.
Distillation also separates liquids from solids. The solids do not evaporate and are left behind after all of the liquids evaporate. Distillation cannot be used to separate the remaining solids. Chromatography separates a solution using a mobile phase and a stationary phase. The stationary phase is a solid that doesn't move, like paper. The mobile phase is a solution that travels through the stationary phase. As the mobile phase travels through the stationary phases, molecules are absorbed in or stick to the surface of the stationary phase. The attraction between the stationary phase and solute molecules competes with the attraction between solvent and solute molecules. The components in a solution travel different distances through the stationary phase. Molecules that are strongly attracted to the stationary phase do not travel very far. Molecules that travel farther have weaker attractions to the stationary phase. Using a different solvent or stationary phase can improve how well the parts of a solution are separated. Solutes will stay in the mobile phase longer if the attractions between the solute and solvent are greater.
I'm going to go back to the quiz now that I know how to navigate. Oh, we'll have to go through. Oh, I don't know if this would be a good idea. I can navigate through. I'm not going to put in any answers, so let's see what we can do. So at least you can figure out, think through, and then when you have access, you will be able to put in your answers. Oh, there we go. Look at, I can preview the whole thing. What I'll do is I will just send you a preview of the questions. And then you can go ahead and answer them into your quiz. I think this is all of them. Yeah. So I'll go ahead and send that to you as well. Make sure I got all of one. There was a little bit more to number one, and here it is. The reading guide. Take a minute to review the answers of your reading guide.
Take a minute to review your answers on the reading guide. You're about to take a quiz on what you just read.
These are the ones that I saved for you because, again, I don't know which textbooks you have. So I saved them both, and I will send them to you. I hope this helps. We're going to go back and just see what we can do. Hopefully this will be helpful to you. I got to find the page that I was on so I can end my live stream here. But I hope this is helpful. If it's not, we'll try something. We'll try and get you up by Monday. Thanks. Bye.